Then we looked at state transition with the control input, right? So then you have two processes going on. One is system is changing on its own anyway. And on top of that, you have some external signal coming in and pushing the state variables to change. So we put these two processes together, and eventually we showed that state transition with the control input eventually will look like this, right? If you have any questions, please ask now before we move on to the next section. So if you look at the state transition equation, number 12 over here, xt is the state, is a vector, okay, at some point of time t. And this is where you start. It's another time, right, t0. So t0 to t, right, this is the transition that happens autonomously, right, without any influence from around, from any control input around. System changes by its own. So this is that part. And then you have the convolution integral. The input comes in and it drives the states further. And this is how it happens, okay? For that period of time, you have to integrate it from 0 to t. Okay. Right. So then if you look at this example here, this is our state space model. You see rate of change of state variables on the left. And on the right hand side, you have state variables or the state vector. In front of that, the system matrix. This is what called the system matrix. Don't get yourself confused. We have different matrices like state transition matrix. And this one is capital A, which is system matrix. And then we have the control signal, right, connected to a second state variable and rate of change of that. So we write it this way. Now, if you are asked to calculate the state at some point of time, right, starting with some initial conditions, right, and under the influence of a control variable, you have to use the system dynamics on this equation, right, a state transition. So two things, state space model and the state transition equation. So our number one priority is this equation actually, right, which tells you xt, right, starting with some initial condition x0. And in the previous lecture, right, we actually derived state transition matrix phi t, right, and there you saw that this was the answer for that. Phi t for capital for simple t time transition. This is the state transition matrix. So if you know t, right, you can actually substitute and figure that out. So there's no problem with this one. What about the other term, second term? Integration, right, phi t minus tau b u tau d tau. Now, because you know a state transition matrix, now you have to substitute for t minus tau. Okay, so this is phi t. So take all the t's out and substitute t minus tau. Because in the state transition equation, what you have here is t minus tau because it is convolution integral. Okay. So then it reads like this. And then you have B, the drive matrix, which is 0, 1, and then U tau d tau. So let's assume some control signal U tau. The most common one is step input, right? So which is 1. Input is 1. So just 1 over here, you don't have to write anything. Then simplify, try to simplify what you have in this integral, right? Now, you can see here the column vector here 0 1 tells you that every time you multiply any element in the first column with this one, it becomes 0. Okay, because this is 0 here. So this term times 0 in the first row, and this term times 0, the second row. So these are meaningless elements, and only these elements proceed from this point onwards. Okay. So what you have is a second element here times the second element here as the first row, and this element times 1 is the second row. So you have that added together and integrate, right, from 0 to t. So this is what you have. All right. So you can see it over here. The matrix that is here is 2 by 2, whereas this is 2 by 1. Okay. So you have 2 by 2 and 2 by 1. Eventually it becomes 2 by 1. Right? So 2 elements. Of course, when you proceed with this system, right, this is a second order system. So therefore, you are bringing 2 elements simultaneously, or 2 rows actually, right? But in the interim, you have these matrices multiplying with other column vectors and all, but it's only temporary that you go like 2 by 2 and others. Once you multiply, it eventually becomes 2 by 1, right? So the first element is this one, which is this element times 1, e to the minus t minus tau, minus e to the minus 2 t minus tau, this one, right? And you can integrate that one. Okay, so when you have 2 by 1 vector that you have to integrate, you integrate the first element and the second element separately. So when you integrate this one, this is the result, right? Check that out. Exponential term, when you integrate e t minus tau, right? And look at you're integrating with respect to tau. So the tau here is actually plus tau, right? So the coefficient here is just 1 because it's plus tau. So when you differentiate tau with respect to tau is 1, right? So nothing is here. But if you look at the second term, when you integrate, right, it is minus 2t minus tau. When you integrate, you write the same thing, right, with the negative sign over here. And then you go to the exponent. There you can see tau. T is a constant in the integration, right? A variable is tau. So it is minus 2 minus t. So plus 2 tau, plus 2 tau. So the coefficient of tau is 2 in this particular case. So therefore, you have to divide it by 2. That's why you have this half here. All right. Then you integrate from 0 to t. So that is the first term. So when you substitute t for tau, right, you get this one. This is 1 minus half. Why? So all the t terms on this side, all the constant terms on the to the front. Okay. So let's take this one. Substitute t for tau. So when you substitute t here, so t minus t is 0. First term is 0. So e to the 0 means 1. And then you substitute tau equals 0. Right? Tau equals 0. So put tau equals 0 here. So it is e to the minus t minus 0. So e to the minus t. And you can see it over here. Right? So these two terms are coming from the first term. And then if you go to the second term, you have this half times this one, and of course with the negative sign. Substitute t for tau, t for tau. So you can see here, uh, uh, t for tau. So t minus t means 0. E to the minus 2, 0 means e to the 0 is 1. So we have this half here, negative half. It comes over here. Finally, you get this term over here when you substitute 0 for tau. So it will be e to the minus 2t to the minus 2t. In front of that, we have half. Okay. This one is positive, this one is negative. All the negative terms. So this is the result, 0.5 minus e to the minus t plus 0.5 e to the minus 2t. So this is the first row element. Okay. And the second row, same process, but slightly different result. And you get this one, e to the minus t minus e to the minus 2t. So this quantity is how much the state variable 1 here and 2 here change due to the influence of the control signal. Okay, due to the influence of the control signal. And you have to add this quantity to autonomous part, how much the system changes its own, right? And then you will see the total change. So when you put the autonomous part, which is this one, transition matrix times state value at time 0, right? Plus how much the system changes, state variables change because of the control signal. So when you put these two together, you get on the left-hand side the final state variables, the values at time t. Okay. So make sure this is not something which you do not understand, right? We have gone through step by step, very methodically. If you have any questions, please ask. And also, I need you to spend a fair amount of time on these derivations, right? Immediately after the lecture today, I can upload this to the Moodle, and you can download and work it out yourself, right? Every line you have to work out yourself manually on paper, right? And then you get a feel about it. Any questions about state transition? All right. So I asked you to, yeah, go ahead.
Yes, sir. This phi value, that means phi equals that matrix that need to be remembered, like kind of like remember, or like it's going to be used from for the futures, right?
What do you mean remember? Because what do you really mean remember?
That
That's not
means
very, there's both of these quantities, this one and this one, of course, right? They're system dependent. So you want to remember how they come and all that, but actual matrix is not anything that is fixed. It changes. Because this one is actually e to the power at. So when a changes, phi changes. Okay.
right.
So for each system, the state equation is different, system matrix is different, and also the state transition matrix, right? So they're all different.
Right.
What remains unchanged is the process, right? Yeah. I suggest that each one of you take a little bit of time and on MATLAB, write down these equations and see the transition for a given matrix, given system rather. You can start with this example, right? And draw it yourself, right? How the state 1 changes, how the state 2 changes, right? See it for yourself. Any other questions, please? Right. So then let us start with the state feedback. Right. So now we can start our next topic, state feedback control. State feedback control. Now you have a fair understanding about state variables, right? Given the system, you figure out, you write down the system equation, dynamic equation, maybe second order, third, fourth, whatever, right? That is a starting point, and then you assign state variables, and you write down state equations, and then state space model, x dot equals ax plus bu, right? Very methodical. Uh, Now, if you want to develop a controller based on that modeling technique, state space model, right? In fact, that has already been done. The simplest one, state feedback control. So that's how we call it. So as the name says, this is feeding back the states, right? You have a very clear understanding about feedback. In the first semester, much of it was feedback, right? But what was fed back? If you remember, it is the response. It is the response, right? So you have the reference signal, you have the response. And let's talk about single input, single output. So you have a reference signal, you have one single output, right? No states, right? Think about an air conditioner, right? You set the reference to say 25 degrees Celsius, and then system gives you some value, may or may not be 25 exactly, right? It changes time to time, and that is the response. You fed it back and compared it with the reference response and see the error, and you design a controller for that. Okay, so that is output feedback, basically output feedback. So now when I say state feedback, now you can understand what it is, right? Now we are feeding back not the output, right, but states. Now if you look at a plant, if it's a second order plant, you have two states. One of them is actually the output, okay? The other one is probably rate of change of the output. Now, in here, we are feeding both of them back. All right. So, therefore, you might get a feeling that this is much strict control system, right? We are not just looking at the output or the response, right? But we are looking at all the other states as well, right? But actually, the concept is the same, feedback, right? Okay. So let us draw a intuitive block diagram, because as I always say, control system is you can start with some your intuition. Okay, how can I control this? And that is the fundamental or compulsory thing when it comes to controls, right? How can I control the plant in a better way, right? You can draw, you can sketch, and then you can put math on it, right? So I draw it like that. I have the system. Now this time is the state space model. So what do I have? X dot equals ax plus bu, right? So I figure out state variables, the rates of change, and then I have a control signal u. So actually u is coming this way, right? I have the control signal coming to the system on the left. So what does it give me? It gives me state variables, x, all right? But it doesn't mean that it gives all of them to me. And if you look at a vehicle, I do have, say, position, velocity, acceleration. Can I measure all of them? Yes or no, right? You can measure the position using GPS. Then you say, okay, I have X position. Velocity, yeah, you can have a speedometer, you can get the velocity. Acceleration, put a little bit of little accelerometer, then you can measure all of them. So every state variable, right, if you want to measure, you need to have a sensor for that, right? And now earlier, it was just one thing, which is output, response. You just needed one sensor to measure that. Now you're going to need n number of sensors to measure all of these states, right? When you deal with state space. So that makes things a bit more complicated and expensive, right? Anyway, uh, uh, for the sake of drawing the diagram, we'll put it like that, x, and we feed it back, right? We feed back x. Now, x is a n-dimensional vector. It has n number of state variables. And then one of them is actually the output, y, right? So the block that select which one of the state variables is actually the output is actually C. Okay, we call it output matrix. In the state space model, you have two equations. The first one is system equation. The other one is output equation. The first one goes like x dot equals ax plus bu. Second one goes like y equals cx. All right. So C is this one, output matrix. And the second equation has another one to make it more complete, plus du, right? That is, if u comes directly to the response output, but you see hardly any plant which has this kind of connection from u to y directly, a link like that, like feed forward link, right? But we don't consider that over here. But if you read books, you will see that one. Don't get surprised. It is for mathematical completeness of the description. All right. And most of the books also where you have this y equals cx plus du, right? Immediately in few lines, they assume d to be 0 and proceed. Right. So this is x feeding back through some gains. Of course, when it comes to controls, you need gains, right? Controller gains. If it is PID, KP, KD, KI, right? So if it is something else, right, you need to have these gains, control parameters to tune the controller for a particular plant, right? So state feedback also has these gains, minus K, because feedback is negative, right? And it goes over here. So the control signal here is actually the inversion of state variables. Now, this is what is called what you call as control law. You need to have some sort of criterion, some sort of some policy, how to generate the control signal, right? Now, if you look at PID, it has a very clear policy. It tells you, okay, if the error is this much and the rate of change of this much, accumulated this much, combine them together through these weights and added together, that is the control signal. Some policy. And then you have to argue whether this is a stable policy, rational policy, and so on, right? You can have any policy. There's no restriction. So in the state feedback, we declare, okay, this is our control law. What is that? U, the control signal, is equal to minus K times X. Minus K is set of gains, X is the state. All right. Now, what is going on in here? Why we call this a good policy? Well, what is the purpose of this whole thing? You have the system, you have feedback, you have the response, right? There's no reference here. Why? What has happened to the reference? This is a bit different from the control systems you have seen earlier, where you had a reference and the error block and output comes in and you compare these two together and generate the error. Here we don't have an error. Can anybody tell me on what assumption can we make this, what you see on screen, is exactly the same control system you have seen in semester 1, where there was a reference, an error signal. Can anybody pick up something from here? And if you look at what we had earlier, right, it's like this, no? Reference, and then this is R, this is Y, remember? And this is E. Now you don't have any of these things. You have Y directly going into the block. So this is the block, controller. Now here we don't have anything. You have the plant. Oops. Right. So this is the plant over here. What's happening here? So let me explain. If you set R equals 0, what happens? If you set R equals 0, when you set R equals 0, right, they're equal. You get this is equal to this, right? You get Y directly coming onto the system. And also there's no controller, right? You get this signal directly as the error goes to 0. The moment you set R equals 0, your reference is 0. Your reference is 0. So therefore, the whole purpose of the control system is to make sure that all the state variables go to 0. Okay, so if I draw time axis, you start x1 and it has to go to 0. You start x2, it has to go to 0. You start with x3, it has to go to 0. Like that, all the state variables, they have to go to 0. That is the purpose of this one. This is what is called the regulator problem. Regulator problem, right? So you have the plant, and the objective of the plant is to maintain the output state variables y at a fixed value. And here we, without losing generality, we call the fixed value 0. But you know, when I say 0, it is a relative 0, right? If you want to maintain a certain level, right, you do the coordinate shifting and make sure that value is actually 0. You deduct some amount, right? So in control systems, when you say 0, it doesn't mean it's absolute 0 anything, right? Whatever value you want to maintain, right, is shifted as 0 by simple coordinate shifting. Now, there are a lot of examples around for that one. Like think about altitude. When you measure altitude, there are various ways to measure altitude. And you can say MSL, mean sea level, or sometimes ground height. If I want to measure height of a tree, I measure it with respect to where I am, ground level, right? From that point to the top of the tree. But if you want to measure height of a mountain, whether it is from the foot of the mountain or mean sea level. So coordinate shifting is happening all the time. So therefore, there's no big issue or any confusion here as to why we set all the state variables to 0. Eventually, this is our reference. Okay, right. So when you see, when you read books also, you will see this one, control low for state variable, particularly state feedback, right? U equals minus kx, right? Don't get upset. This is the regulator problem. Now, if you think of fast changing references, right? It looks like this is not going to be able to handle that situation, right? But it is actually not very true to say that if the reference is changing all the time, right? Once you change the reference, you keep it there for some time. Any plant is like that, right? If you want to move, let's say, an arm of a robot by 30 degrees, right? You send 30, but you keep the 30 intact for at least some amount of time, right? Giving that time for the controller to move it by 30 degrees. And after that, only you put another command. Now go to 45, whatever, right? So during that time, your reference doesn't change. Maybe it's a small amount of time, but for the control system, it's long enough to drive the variable to that reference level. So if you look at that level, it is a regulator problem. But if you come out and see the whole process, it's not a regulator problem, it is tracking problem. All right. So if you have a very good plant where tracking performance is good, its regulator performance is also very good. In fact, you design the regulator problem, right, and get better result from that, and then you can put it into tracking problem. Okay, so I think so much for that. We can move on. So I think we have no problems as to why we close the loop this way without the reference. And also our control law u equals minus kx is logical. Why? If you want to set a variable to 0, what you need to do when the variable is positive, you need to give a negative command to bring it down. And if the variable is negative, you got to put a positive command to push it up. So therefore, your control signal should be in opposite sign of the variable. That's also logical. And that's why we have this negative k here. Okay, right. So that's good enough. We have a good policy and feedback control law, right? And this is state feedback. Now, if you look at these ones, K is the state feedback gain matrix. K is a column vector, K1, K2, like that, right? X, well, you basically, when we declare a vector, we write it as a column vector, okay? But when you put it into manipulation, you have to put it in a row form and other forms, right? Okay. So what do we have here? So this is our state space model, x dot equals ax plus bu, but u is minus kx. Okay, so we substitute for u, and what comes over here is minus k times x. So when you simplify this one and put it into Laplace, x dot becomes s times xs minus x0, right? Initial condition. Then axs plus b minus k xs. So put all the xs terms to the left-hand side. This one goes to left-hand side and then comes back onto the right-hand side as the inversion. And x0 is the initial condition, comes to the right-hand side, right? So now if you want to evaluate the inversion here, matrix inversion, you need to write the cofactor matrix over the determinant, okay, times x0. So now for any plant, right, if you want to investigate the behavior, the performance and all that, there's one place you need to look at, and that is nothing but the characteristic equation, okay? So if you see the characteristic equation and if you see the poles in the right places, you are happy. So if you look at this one now, right, the characteristic equation in the previous slide, you saw that it's a determinant of Si minus A plus Bk. Now you look at that. K is part of the characteristic equation. So we are happy, right? The low, the state feedback policy we came up with is actually working, because now you have this K as part of the characteristic equation. All right. So now we know that by we can leverage on these values, feedback gains, in order to shape off the characteristic equation. Okay, and actually place the poles wherever we want. Now again, if I tell you this in a slightly different way, the whole purpose of designing a controller for a plant is to place the closed loop poles in the desired positions. That's all about the whole purpose of designing a controller. In the the closed loop control system, if you have your poles in the desired positions, you get the best or appropriate performance. So through the gains and through the feedback, what we are trying to do is probe into the closed loop poles to see where they are, okay, and move them and locate them in an appropriate manner. Now, this is a variable characteristic equation, right? You can mold it into various shapes. So let's assume, right? Okay, I want to place my poles in these positions, lambda 1, lambda 2, lambda n. It's a n-dimensional system. There are n poles, and I dictate, I want my first pole to be this location, second pole at this location, like that. Because poles means you know your response, what is coming out of the plant, okay? So now you can equate 1 and 2. This is the characteristic equation of the plant with state feedback, and this is the desired characteristic equation. We want to get this characteristic equation after all these things, right? Loop shaping, gain tuning, everything. I want to get my poles located at these locations. Right. So I can then write 1 is identical to 2, right? And find out K1, K2 up to Kn, all the gains. So this is what is called the pole placement using state feedback. Okay. So I place the poles, lambda 1, lambda 2 up to lambda n. I place the poles at right locations using state feedback, right? This formulation. So then I calculate K1, K2, K3 up to Kn. Okay, what are these values? So this is a simple example for you to understand how the state feedback works. So it's a pendulum. Everybody knows about pendulum. You have done this, I think, A-level physics, right? So this is the pendulum, length L, mass M. The stick has no mass, right? It's weightless. And then you can draw the direction of motion and the weight component along this motion, which calls the circular motion, and write down these equations, right? Go through that when you have the copy of this document, and get these equations. L theta double dot is equal to minus G theta, right? It's a nonlinear plant in a way, right? But once you simplify, you get to a linear model of the plant, right? So, and then turn into a state space model, you will see this one, right? Let us call theta as the first state variable and theta dot as the second state variable, right? So it's a second order model. X1 dot X2 dot is equal to system matrix times X1, X2. Okay, fine. So now You can actually write it this way. This minus G over L is actually omega 0 square, the resonant frequency, right? Or frequency of oscillation. Right. Now, if you want to use state feedback to locate the closed loop poles at minus 2 omega 0, I want you to change the system into different pendulum, right? With some force coming from outside, right? To accelerate the angle, right? Some sort of force coming from outside. You design a control law to get this additional force onto the mass, right? To make it behave like a different pendulum, right? So how do you do that? Now look at the characteristic equation, Si minus A plus BK. So A is over here, B is over here, right? The force is actually being is applied on x2 dot, x2 dot. If you look at x2 dot, right, it is theta double dot. Some sort of torque, right, you produce as the whole thing swings. So get the characteristic equation Si minus A plus BK, right? The determinant of that is equal to 0. So you get A from here, right? Plus this is B, K is K1, K2. Right? Now you put it like a rho is equal to 0. You get this as your characteristic equation, right? Now, what is your objective here? Your objective is to locate your poles in a specific locations, right? Now, let's first work out this characteristic equation, determinant of this one, right? Over here, right? You know how to do that, right? Calculate the determinant of a 2 by 2 matrix, right? Diagonal elements you cross multiply and then negate them, right? So this is what you get. Number one, equation number one is the characteristic equation of the pendulum, right? With state feedback. You can see K1, K2, we have two gains because we have two state variables, theta and theta dot. And we have two gains, right? K1, K2. So when you measure theta 1, you multiply with K1. When you measure theta 2, you multiply with K2. Right? Then add them together and put a negative sign, feedback. And that feedback signal goes as a torque to the pendulum so that it will change the acceleration of the pendulum. Now see how this works, right? You measure position and velocity and then multiply with two gains, add them together and get the negative sign, produce a torque, right? And you're changing your pendulum. Now, your desired characteristic equation is this, right? Because it said you want to locate the poles at minus 2 omega 0. Now frequency of oscillation, right, is omega 0, this one, right? So whatever comes over here, G over L square root is the frequency of oscillation. And now we want to double it to make it go fast. So you're designing a state feedback controller for that. Okay. So the desired characteristic equation would be is this S plus 2 omega 0, S plus 2 omega 0. When you multiply, you get this one, equation number 2. Okay. If you know the poles of the plan, you get the first order blocks, multiply together, and that is the characteristic equation. So equation 1, 2, you're talking about the same thing, right? You equate them, and you can see S square square, K2S, 4 omega 0 S, K1 plus omega 0 square, 4 omega 0 square. So when you equate the two together, 1 and 2, you can write down this equation. K2 is equal to 4 times omega 0. Omega 0 you already know, right? That is square root of G over L multiplied by 4. And that is your gain K2, state gain K2. Then the other one is K1 plus omega 0 square is equal to 4 omega 0 square. Then you know K1 is 3 omega 0 square. And the entire gain matrix is this. So all what you need to do is get your state measurements, right, angle, multiply with this one, and then get the velocity using, say, a tachometer attached to the pendulum that gives you the velocity, angular velocity, right, and multiply with 4 omega 0. And then add them together, put a negative sign, you get the torque. Okay, right. The moment you do that, you see it's another pendulum, but different to what you had. Any questions, please? Is everything clear? So let me ask from few of you, Tamira,
Okay, sir. Yes.
state feedback, state space modeling, and gain calculation using state feedback. Is everything clear?
Yes. And some things we after rewatching this, it's okay, sir. Most of the things are clear, overall clear.
All right. So if you have anything that is not clear, you can ask now. And Vihangi,
Yes, sir. Most of the things are clear.
everything clear? Right. Yasiru,
Uh, yeah, like due to some reasons, I missed few lectures, so I'm like rewatching things. So little bit there are some things I couldn't understand, but I think after watching the videos, I can get understand it.
I understand that, but um, watching the videos later and try to understand, of course, you need to do that, but this is the precious time for you to ask questions and get things that you are not very sure about, right? Clarify all these things, because one of the dangers of self-learning is extremely important, right? Because you cannot expect somebody teaching you lifelong, right? So basically, teachers are only to guide and give you some specific directions and explain you concepts and all. But much of the labor is basically on self learning, right? We train you to be self learners. But having said that, there's a little danger also. Uh, when you learn yourself, you are not going through a straight line. Whereas when you do the guided study, you go through a straight line. You don't go here and there, right? But self-studying, you can go this way, that way, and then later you figure out, okay, my understanding is not correct. So therefore, it goes like in spirals or zigzag, right? So it takes a little bit more time, therefore, but it's good practice. So you need to have a very good compromise between, say, guided learning and self-studies, right? So, but I have seen some students, they have more faith on learning later, right? Going through the videos and all that, but they are clearly missing something very important, right? You can cut down your learning time, save your time, right? If you get as much as possible in terms of content through the lectures, right? This is not for only for Yasiru, but for everybody, right? If any one of you think that, okay, I can read the lecture later and understand, you are not very correct in that decision. So therefore, when you come for the lectures, make sure you have reviewed the previous lectures and all, right? You are ready to go with the present lecture. If you want to get the maximum absorbed, right, you need to come prepared for the lecture and ask a couple of questions, and then you are okay, up and running. So sometimes you don't need to spend a lot of time during the week before the next class. Right. Dhananjaya, how about you?
Yes, I got it. But here's a with the K1 and K2. Here's a K1 equals to the 3 omega naught squared, and K2 is
Right.
going to be equal to 4 omega naught squared. That means
Okay.
it's like kind of like two units actually.
Yeah. Yeah.
Like that's is this due to x1 and x2 being like the derivatives of, like we have seen that x2 is the derivative of x1 and so on.
Yeah. Now, variables are related that way. The second variable is actually the first derivative of the first variable, right? Because they are lined up that way. Because we want to have this very systematic way. We don't want variables to be totally independent from each other, so that you can't do anything about it, right? Because there's a lot more to be done later when you think of this optimal control and all that, right? This is just the foundation. When you have the variables defined that way, you can bring it further up and develop. None of these controllers are optimal, right? But they do a good job, and you get your poles located at desired values. But there's no assurance whether this is the optimal controller, which means is this the controller which brings the system from one state to another in an optimal manner, consuming as less as possible energy, right? Or in minimum time. No, there's no such constraint or policy in these controllers, but they're coming, right? They're there. In that case, you want to write down equations combining all these things: initial conditions, control signal, state variables. So if you don't have these relationships, you cannot remove some of the variables and substitute from other variables and all that, right? Things will be like unrelated variables in the plant. So it will be difficult to handle. That is why we prefer that way. So it is very systematic. You have a lot of relationships between state variables, so that using these relationships, you can remove uh, some of the intermediate variables and relate, say, initial condition and the control signal or the final state, like that, and design an optimal control, right? So that's why these two gains are actually 3 and 4 is just a coincidence, probably, right? It could have been anything. So there's no such relationship there between K1 and K2. Just for this one, because of the nature of the plant, it came like that. Okay, is that clear?
Yes, sir. Okay.
All right. Now, you have this example. Maybe we can take a look at that. Design a state feedback regulator for the system. So here I have specifically written regulator. Now, when I say regulator, you know what it is, right? It's like the voltage stabilizer at your home, if you have one, right? Voltage stabilizer, right? It works in between the wall outlet and your electrical system to make sure the system is always 230 volts at 50 hertz, right? But most of these voltage regulators, they only do the voltage regulation, not the frequency regulation, right? Frequency can vary a little bit, but that is done by the electrical power system. Make sure that it is 50 plus or minus maybe 1%, okay? The stabilizer is basically voltage. What it does, it makes sure you have 200 whatever, 30 or 10 volts, right? Single phase. If it goes up, it brings it down. If it goes down, it brings it up, right? That's the whole purpose. Maintain at that level. So now you can assume this 230 RMS volts is 0 here, okay, by shifting the coordinates. So the whole purpose is to keep it there at all times. And if there's a little disturbance, it will intervene and fix it at that point. Okay, so this is our plant x dot equals ax plus bu, and this is a third order system. And this is the C matrix. You are picking up the first state variable as your output. Okay, and place the closed loop poles at -2 plus or minus J4 and -10. So because the system is third order, you have 3 poles, and you have 2 poles like this, a pair of conjugate poles, and then you have a negative real pole at -10. How do we do that? I think it's very simple, right? You have gone through one of these things before. Let's use the state feedback as u equals minus kx. You use this control policy, right? And this is your gain matrix, or rather vector k1, k2, k3. The process is very simple, right? Process is very simple. If you draw a block diagram for the controller, right? This is our x dot. It when you integrate x dot, it becomes x state variables. State variables multiply with system matrix A, and then state variables get multiplied with minus k. This is the feedback, and it goes through B, added together, and that is the x dot. If you look at this equation, that is what it is. X dot equals ax plus bu. All right. Now u equals minus kx. U equals minus kx. So you have 2 paths, right? When you add them together, it is equal to x dot. So this is what I have drawn here. 2 paths, when you add them together, is x dot. One path is basically ax, right? Autonomous path, and the other one is the exogenous path, minus kx times b. And we send x to C output vector to produce y. So it's not a must to draw this thing, but it's good to have this practice to see how the variables move around and how the feedback happens and all. Right. Now, closed loop poles, they're located according to the characteristic equation, which is Si minus A plus Bk determinant, right? And when you write it down, break it up like this is Si, third order, minus A, system matrix, plus Bk, B times K, right, is equal to 0. You get this matrix. And now you want to get the determinant, right? Now here, down here, I have put this one reference for you to refresh yourself about how to calculate the determinant of a 3 by 3 matrix. So like, say, for example, this one, 3 by 3 matrix. If you want to calculate the determinant, you can pick up a row or a column or whatever, right? And here is probably have taken the first row, 1, 3, 2, right? You take 1 and then remove the row and column, right? With that element being common, and take the other remaining partition, which is -1, -3, and 3, 1 as a 2 by 2 matrix, and get the determinant of that, multiply with this one. So it is 1 times determinant of this small matrix, 1, 1, 3, 3, right? And over here you can see it is you multiply the diagonal -1, 1 over here, then you put a minus sign, multiply the other opposite diagonals, 3 times 3, -3. So it's minus 9. Okay, first term. Then put a minus sign. All even terms are negative, all odd terms are positive. So this is the first term, odd term, plus this is the second term, which is even. So there's a negative sign here. Then you pick up the second element on the first row. This is 3 here, and remove this row and this column. And what you remain with is 2 by 2 matrix, minus 3, 2, 1. So minus 3, 2, 1. Right? Then multiply the diagonal 1 times minus 3, and the other one is 2 times minus 3. So you can see it over here. In front of that 3, multiply it. So this is the process of calculating the determinant of a 3 by 3 matrix. Okay, right. So when you do that, this is the result you get. All right, so just leave it aside. Make sure you do all these things manually at home, right? I don't want to work it out here taking time, because very obvious things. You can check that out. Now, there's a desired set of poles, right? In this example, they are minus 2 plus or minus 4j and minus 10. So with that, you can write down the characteristic equation, right? So line them up. First pole, second pole, third pole, and s minus first pole times s minus second pole times s minus third pole, and multiply them together. So you have your characteristic equation straight away, right, from the desired poles. And you have the characteristic equation from the state feedback path. So both paths lead to the same thing. So if you take the desired poles and write down the characteristic equation, you get this one, this polynomial of S. And when you compare this one with the previous one, number 1, right, S to the 3, S to the 2, S and constant term, respective coefficients, you can actually compare and write down a few equations with K1, K2, and K3 and solve for them. And this is what you get, 6 plus K3. So this is coming from, say, the second term of the polynomial, which is 6 plus K3 times S square. And here it is 14S square. So therefore, 6 plus K3 should be equal to 14. So you find K3. And look at the third term, which is S term, 60S here. And here it is S plus K2. So S plus K2, sorry, 5 plus K2 is equal to 60. You can calculate K2, and same way you can calculate K1, has to be 199. Very simple, right? You can calculate all these gains, K1, K2, K3, so that you can implement the state feedback controller. So this is the gain matrix. So you put it over here, right? You know A, you know B, now you know K, and you can simulate the plan and see how it works. So in MATLAB, please do this yourself, right? I'm not going to check, but it's really good if you do that. You define your system matrix A like that, and the drive matrix B like that. And this is the desired poles P, right? Minus 2 plus J4, minus 2 minus J4, and minus 10. This is also written as a vector. Okay. And you say K equals place ABP, pole placement. So this matrix in MATLAB, this command in MATLAB will work out this process. You have the two equations and you calculate the gains. Okay, so MATLAB has this already pre-coded, and name it as place command. MATLAB place command, pole placement. So once you give A, B, right, and desired poles, it will calculate the state feedback gains. Right. Now, let's look at pictorially what's happening here. Now, this is our plant. X dot equals ax plus bu, and it produces, say, x dot, right? Because now you have x coming or from here multiplied with a, and you get the first element here, ax. And also x goes like this through k, you get kx, and it's negative now. Say, let's say r equals 0, and it is u, right? U multiplied by p, and it produces the second term here, bu, right? This is the first term on the right hand side. This is the second term on the right hand side. When you add them together, x dot. All right. So x dot, when you integrate, becomes x, right? And then when send it through c, you produce y. And this is the d term, which we do not usually consider here. We set d to 0, but to be complete mathematically, some books have written this path also, du. U comes straight away to y. Right. So, if you write down the control law, which is state feedback, it is basically R minus Kx, right? R minus Kx, K times X. And again, RT is set to 0. All right. So it is here because even though I have already explained, maybe later you might be watching where is the reference, right? So for that reason only I have written it here. Right. So so this is basically how the whole system is written using state feedback, and eventually you get a minus bkx plus br, the reference, because r is 0, don't have to worry about it. So if you look at the actual system where you have some reference, right? Some reference, it goes like that actually, right? The reference changes and system is tracking the reference. But now when you say set r equals 0, which means you adjust this time to time to make sure when you get a new reference value, non-zero value, you immediately adjust the coordinates so that the new 0 is the reference, right? So then what you see is over here. It remains at 0 and there's an error. In fact, what we really want to monitor is the error, not the reference, right? Reference is a hidden variable. We really are concerned about the error, right? We want to see this one. Don't want to see the reference together with the actual, right? As long as the error is presented, it's good enough for us and it's very clear. We need to deal with the error to reduce as much as possible. Okay. Right, so let's take a little break over here before we get the aerodynamics. All right, welcome back. So what we are looking at here is what is called aerodynamics. Now, what is aerodynamics? For any controlled plant, right, there's an error, right? Error is the reference minus actual. And the rate of change of error and how it changes and how it is related to the error, right? And that is what is called aerodynamics. It's like dynamics of the error, right? Basically. So with your understanding about system dynamics, how the state variables change, right? There you saw the rate of change of state variable 1 is related to state variable 2 and so on. So some sort of dynamics, right? So that you can predict what's going to happen to the state variable in a future time. Error dynamics also, if it is available to you, right, you can look at it and figure that out, whether the error is stable and converging. So if you see the error dynamics converging and stable, then that's kind of proof that you have a good system. So whatever your tracking process is taking the system to, right, error reduces in between, right? And every step of the way, error converges to 0. And then there's a disturbance, there's an error, but gradually or quickly, right, that error will be eliminated. So this is kind of embedded process to the plant now, because when you operate plants, right, you change your reference, right, and sometimes there are disturbances. There are a lot of changes are happening, but we need to have some sort of assurance that whatever happens, right, deflections, that particular error that is generated at that moment where there's a deflection or set point change, that error, right, quickly converge to 0. So that is very important thing to know about any plant. Now, in order to get to the error dynamics, you need to have error rate and error, and then try to figure out how they are related. So for that, we use these equations. Say, for example, equation 3 here, rate of change of state vector, right? All the states, their rate of change. You have this equation, a minus bk times x plus br. Now, if you set your time to infinity, right, the equation will change like this, x dot infinity on the left hand side. So we are basically referring to this equation, right? When you bring time to infinity, this becomes x dot infinity, right? Rate of change at infinity, right? And also here x becomes x infinity, like that. So you get this equation, equation 4. Now, what is this infinity? Again, infinity is a relative term, right? Relative term. So if you think of, if you ask from an ant, right, what is your infinity? For an ant, it would be like few meters, right? Or maybe more than that. Ants walk very fast, right? Maybe a kilometer would be infinity, right? For an ant. But if you think of an eagle, right, the infinity is much farther away. So infinity is like the relative term. When it comes to control systems, right, you see the convergence, right? When you change the reference, the response tries to reach the reference, and then it settles there. Any time after that is infinity, right? In control systems, the meaning of infinity is that up to that converging point, okay? So for a very fast servo systems, infinity can be less than a second even, all right? So before you get the next control signal, system is already there. It has reached to the given reference within that time window, and it is waiting to receive the next signal, right? In between two uh, reference inputs. So therefore, don't think this infinity is actually very, very long time. It is within the sampling interval. It is within the sampling interval, right? So now, if you look at on what is on the left-hand side, equation number 4, x dot infinity, And this one, x dot t, right? So it is the actual rate of change within that very small time window. It's not a fixed value, it is changing. But this one is a fixed value. After converging, it's not going to change, right? It's a fixed value. So in fact, that is the reference kind of thing, right? Where it settles eventually. And before that, for general time t, the rate changes. So all the time. So if you get the rate of change minus x dot infinity, it is actually the rate of change of error, right? Like this, x dot t minus x dot infinity. And also on the right-hand side, you have x infinity, which is a fixed value where it settles, right? Within that sampling interval. And if you come back to this equation, you will see xt, right? Which is varying before it settles. So once you get the difference, it is in fact error. This one, xt minus xt infinity, right? This is error. This is error rate. So you have a very simple relationship here between error rate and error, like this, a minus bk et. And we call this error dynamics. I am sure you have seen similar equations in the first semester, right? And also in the discrete format early this semester. When you see something like that, a minus bk, right, as a connection matrix, and after that you have error et, and on the left hand side error rate, you know that this is converging. And if you want to see a little bit more details, we can bring it to Laplace like that. So s times es minus e0 initial error is equal to a minus bk times es, and combine es terms, and the common factor would be si minus a plus bk, and when bring it back to the right hand side, it will be inverse of that, e0 initial condition. So the moment you change your reference, there is a big error, right? This is that error. But during, if the system is stable within that sampling interval, right, because of this dynamics, right, and how you have set your k, b, a, error will go to 0, right? So before you get the next reference signal, after one sampling interval, system is settled there. So this is what you really want to have in your feedback control system. So in order to achieve that, how fast you converge your error to 0, and what is the remaining time until you get the next control signal, right? So that depends on A, B, and K. A, B, and K. Any questions, please? All right. So that's it for that lecture, and let us start with the next lecture. That is basically controllability and observability. All right.